All right, welcome back, grade 12s. Today we're going to be finishing off chapter 5. We're skipping 5.4, but going straight to 5.5. But I wanted to do an example for you that's like what they did in 5.4 to make sure that you understand how to tell the difference between these two options. So I just made up this question. So pretend you were given these two methods for saving your money. You have $1,000 and you can put it into an account that pays you 4% simple interest, and you are going to put it away for 5 years versus the same $1,000 at 4% interest, but it's compounded annually for, again, 5 years. So it's important that you understand what these words mean and how to apply it to get your new amounts. So you can see I made these two tables. This is table 1 for option 1, and this is table 2 for option 2. So here we have the year 0, 1, 2, 3, 4, 5. So you just walk to the bank and you just put away your money. You only have $1,000. 1 year later, you're going to earn 4% extra. So 4% as a decimal is 0.04. So we're going to times that by $1,000. And if you're not sure how to do that or what that's going to give you, just jump the decimal place 3 times. 0.04 times a grand. And again, there's your 40 bucks. So you're going to get an extra 40 bucks, which means your total amount now is going to be 1,040 bucks. Now, the next year, again, you're going to earn 4% on the $1,000 you originally put in. So not this new amount, but your original amount. So simple interest is only based on the original amount that you invested, not your new total. So even though this extra $40 is sitting in the account, it's not actually going to earn you any extra money. You might as well go and withdraw the $40 because all that's going to matter is the original $1,000 that you put in there. Now you notice we had to do the adding separately. In order to make this go a little faster, we could just change the 0 in the front to a 1 and write 1.04 times the original $1,000. And when you do that, you notice that it's going to do the adding for you to give again your new total. So this gives you 1040. Well, that's what we got the last time. So we just added our extra 40 bucks. But that extra 40 bucks from before is still there. So technically you have 1080. So the extra plus the extra will now give us 1080. And I'm sure you're getting the point now. We're adding 40 bucks each year, and that's all we're ever going to add. So we just keep adding 40 bucks. Add an extra 40 bucks. And add an extra 40 bucks. So if I asked you what type of data this was, you would have to find your first differences. So 1040 minus 1,000 is $40. 1080 minus 1040 is $40. 1120 minus 1080 is $40. And you can see that it's 40 all the way through, which means this data is linear. And this is showing linear growth because the money is increasing, so it is growth. If you were to graph it, it would be a line. So if we had money and time on the X and the Y axis, we would start at $1,000 and then it would rise the same amount every year. So up 40 over 1, up 40 over 1, up 40 over 1. So that is definitely a linear situation. So simple interest is linear. Okay, I want you to always remember that. Now in the other situation we have here though, it's not simple interest. We again start with $1,000, but it says it's compounded annually. So you're going to see what that means. So it's still 4%, and I want to add the 4% on. So we have $1,000 times 1.04, right? The 1 makes it add on. And you're going to get 1040, just like we got over here. No difference. The only difference now in this situation, the word compounded means your new start amount for the next year is not going to be 1040. It's not going to be 1,000. It's going to be 1040. So your old amount now becomes your new start amount. And you're still going to add on 4%. So 1040 times 1.04 gives you 1081 and 60 cents. Now that 1081.60 now becomes your new start value. And that gives you $1,124.86, which then becomes your new start value. $1169.86, which then becomes your last start value here. And remember, money always has two decimal places, $1,216.65. So 1216.65. All right, so you can just tell we went up by 40 here, but here we went up by $41.60. And then here we went up by even more. So you can see that the first differences won't match. So this is definitely not going to be a line like this one was. Second differences, I can tell you, will not match either. So this is not quadratic. So let's find the ratios. So remember how we find ratios? It's y2 divided by y1, y2 divided by y1. So what's 1040 divided by 1,000? What is 1081 divided by, so let's use our cents as well. $1081.60 divided by 1040. 1124.86 divided by 1081.60. 1169.86 divided by 1124.86. And the last one, 1216.65 divided by 1169.86. So if you go down and you divide y2 divided by y1, y3 divided by y2, nothing too shocking is going to happen. You're going to find that you end up with 1.04 or roughly 1.04. Now remember that we rounded a little bit. Which is 1124.86 divide 1081.6. Now let's see, so 1.0399, it's the same as 1.04. And they should all be 1.04. So this data, because the ratios all worked out to be the same, is exponential. And you can tell by that word compounded. So it's exponential, and again, it's growth. And the key word was compounded. I'll explain more once we get into finance later on. So when you graph it, it's going to start off slow. So again, time, money. You start off at 1,000, and then it's going to grow a little bit, very slow, and then it's going to increase drastically because it's building on itself. So this extra 40 bucks and then the extra 41 bucks, that extra 40 bucks is always earning you more interest. It's embedded in your new amount. So it's always going to be earning you 4% every year because it's added on into your total. Whereas in simple interest, you're always starting back with the original amount. That money that you made as interest doesn't do anything. It just sits there as dead money. All right, so that was just a little review of how we do our data tables to determine what type of data we have. Now, in the content section, you will find 5.5, how to select the correct model. It's there for you to print, copy out, do what you want with it. So it's listed in the contents area. Also, your homework is found on page 97. I'd like you to do questions 1, 2, 3, and 4A. All right, so if a population grows by each percent each year, what is the factor as a decimal? Basically, convert percents to decimals. So you know that as dividing by 100. So jump the decimal place twice to the left, 2 jumps to the left. When you divide by 100, 2 jumps because of 2 zeros. So 30% would be 0.3, 75%, 0.75. 4%, jump once, and then you run out of numbers, so you put a 0 there. So not 0.4. This is 40%. That's a different number. 0.04 is 4%. Now 3 1/4, that 1/4, it's probably easier if you wrote it as a full decimal like that. 3 1/4% is 3.25. Again, jump once, jump twice. So it means you need to put in a 0 as a placeholder and then copy out the rest of the numbers once, twice. There's your 2 jumps to the left. And that's how we turn percents into decimals. Very important, especially when we deal with money. All right, so when you're selecting the best model, it's important, again, you look for some keywords. So what type of growth does each scenario show? A hairdresser increases the price of a haircut by 50%, 50 cents, each year. So she's doing it every year by the same amount. So that means that it's constant growth. This is constant growth. So 50 cents each year, this would be linear. Terry's investment doubles each year. So this means that whatever the investment was here, we times it by 2, and then we get a new answer. And then we times that one by 2, and we get a new answer. This is exponential. Right? When you multiply or divide to get to the next number, that's exponential growth or decay. Players in each round of golf are the winners from each of the pairings of the previous round. So this is like a Final Four situation where these 2 teams play, these 2 teams play. Whoever wins out of these 2 goes on. Whoever wins out of these 2 goes on. So right away, we see that 4 teams became 2 teams, and then these 2 teams play each other. And then what's going to happen is you're going to get 1 winner overall. So this means 4 became 2, and 2 became 1. Well, divide by 2, right, to get to the next amount. And again, because we're dividing by the same amount, this is exponential again. This is decay though. Daryl makes $10 an hour plus a weekly salary of $250. So this is linear. We have a start amount, $250, plus an hourly wage. So that's the rate of pay. So that's what those situations show. Now here we have equations. So put an L for linear, put a Q for quadratic, and put an E if it's exponential. 2 times 4 to the power of x. Now the x is here in the exponent part, so that means that is exponential. 2 plus 4x squared. That 2 tells me it's a second degree function, and because it's a second degree function, that tells me that it is quadratic. 2 plus 4x. So you notice that all the exponents are 1. That tells me that it's linear. And this last one here, 2 bracket 1 over 4, and then up in the air, x plus 5. The fact that there's an x up in the air tells me that it's exponential. All right, so that's how you do it from words. That's how you do it from equations. All right, City Council wants to discourage illegal parking. They have 2 plans for fines. $10 fine for the first offense, and then it increases by $20 each time thereafter. So the first time you get caught, it's going to be $10. And then it's going to increase by 20 for each fine thereafter. A $10 fine for the first offense, which then doubles every time thereafter. So this one, it's going to start with a 10, but then it's going to be multiplied by 2 every time you do something wrong. Okay, so you see the difference in the equations? This is 10 plus 20 each time. This is 10 times 2. That word doubles tells me it's times 2. And the number of timesing of 2's is going to depend on how many times I get fined. So, which type of growth is this? Well, it looks like linear because we're adding the same amount. We already developed the equation. So the money, the cost, is equal to 10 plus 20 times each number of times I get fined. The second one looks like exponential. And that word double told me it was exponential. And again, the equation, the money I'm going to have to pay is equal to 10 to start, doubling each time I get fined. All right, that's pretty much all I wanted you to see out of that one. Use your model to predict the fifth infraction. So again, you would sub in 5 into the first equation and into the second equation to work it out. When you do this last one here, oh, well, this question just says, which one do you think is better at deterring illegal parking? Well, my guess would be the second one, because the money probably grows very quickly because it's being doubled. And that means people who are consistent offenders are probably going to stop because it's going to end up costing them a lot of money. When you end up doing these, notice you have two tables. If you want, I would probably do your tables out like this, because that's probably the way you're used to it. So 0, 1, 2, 3, 4, 5, and copy out the numbers 400, 420, 441, and so forth. 486.2 and 510.5. Figure out your first differences, figure out your second differences if you need to, and do your ratios if you need to. Now remember, you only do first, well, you do first difference to see if it's linear. Doesn't look linear to me right away. You do second differences of your first differences if it's not linear, and then you move to ratios if none of these work. Ratios just means this number divided by this number divided by that number. And that's what you put down here. This guy looks like exponential to me. He's swooping up pretty steeply. This is obviously linear. This looks exponential to me as well. He's swooping down. And this one you won't know again until you do the table and your first, second differences and your ratios. So I hope that helps when you start going through the practice questions on page 97. Again, 1, 2, 3, and 4A. Let me know if you have any questions, and there'll be some more work coming on later in the week that I'll want you to hand in, and I'll let you know when that's happening. All right.